In this video, we're going to have a look at solving a vector-related question in which we've got an aeroplane flying at 400 knots and there is a northwesterly wind of 50 knots acting on the plane. The pilot wishes to fly in a due west direction, and what we need to obtain is which direction should the pilot fly at the 400 knots in order to achieve that direction, and with the effect of the wind, what's the resultant ground speed going to be? So first of all, I've set up an axis system, so I've based it on north, south, east and west coordinates, and we need to start plotting our vectors. So the first one that I'm going to plot is actually, I'm going to plot the resultant flight on here first of all. So we know that the pilot wishes to be flying in a due west direction. So we could plot on here that our resultant is in that due west direction there, going from the 0 in the due west direction. So we know that the plane is flying at 400 knots. We don't quite know the direction, but we know that it's going at, so we go from here, going say over to there, and that's 400 knots. So we've got a length on that vector of 400. The wind speed is 50 knots and it's a northwesterly wind. So when you're referring to wind speeds, a northwesterly means that it's coming from the direction of the northwest, and therefore it will be blowing the plane in the southeasterly direction. So if we kind of draw a mini north, south, east, west coordinate system at the end of our plane, the wind direction is then in a southeasterly direction. And the resultant of those two will give us the resultant of the flight of the plane. So the wind is going in 50 knots in that direction. So now we've got our vectors plotted out. Let's put in the information that we know or that we don't know, as the case may be. So we've got the length of that blue plane vector at 400 knots, but we don't know the direction in which that pilot has to go. So let's call that angle alpha. So we don't know what that direction is. We do know that the wind speed, which has got a length of 50, we do know that is in a southeasterly direction. So if it's in a due southeast, then the angle between the south direction or between the east will be 45 degrees. So it's as it's a due southeasterly wind, the direction between the south axes will be 45 degrees. And then the resultant R, we'll call that one R. We don't know the length of it, but we know its direction is in the due west, which is why we've put it on that west axis. Now the method that I'm going to use to solve this is by resolving each one of those vectors into horizontal and vertical components. So first of all, let's take the speed that the plane is currently going, so that's 400 knots. Let's just draw ourselves a small right angle triangle over here. So as I say, we don't know the angle, we'll call that alpha, but the length of the hypotenuse is 400. So we've got the, we'll call that one plane horizontal, so PH, and the plane vertical. So if we resolve that into the horizontal and vertical, we can have the plane horizontal is equal to the hypotenuse, which is 400, times, and it's the, so we're looking at the horizontal, which is the adjacent, so 400 cos of alpha. And the vertical component, so plane vertical, that's going to be the hypotenuse, which is 400, and then we're looking at the opposite to the angle, so that will be 400 sine alpha. Then let's have a look at the same for the wind speed. So let's draw out a right angle triangle for our vector representing the wind speed, and it's a 45-degree angle, and the hypotenuse, so the length of that vector, was 50. So we can have the horizontal component for the wind, WH, and the vertical component. So the horizontal, WH, this is going to be the hypotenuse, which is 50. In this case, it's actually the opposite, so 50 sine 45. Although, of course, with a 45-degree triangle, the sine and the cosine are the same, because the other angle will be 45 as well. And then the vertical WV will be 50 cos 45. Okay, so that gives us our horizontal and vertical components of the plane and the wind speed. Now our resultant, R, this is acting in the due west direction. So if we think about it as a vector on its own, let's just draw it out. So this is our R length vector. We can't draw it out as a triangle because there is no vertical component to that. So if we were to calculate the resultant vertical, there's no vertical component to that vector, so the resultant vertical actually is equal to 0. But we know that the resultant is a combination of the vertical components of our plane and the wind speed direction, so we can use that to calculate this unknown value of alpha. So if we look at the vertical components, we've got the plane, which is flying. Let's just set our axes system. Let's have up as positive, and let's have direction to the left as positive. So I've gone with the dominant direction there. So looking in the positive direction, resolving our vectors for the vertical components, we've got that the resultant vertical is 0, but that's going to be equivalent to the plane vertical, which is 400 sine alpha, and then the wind speed vertical acts in the opposite direction, so that's minus 50 cos 45. So you can see now that we've got an expression formed here. 0, so looking at the vertical, 0 equals 400 sine alpha minus 50 cos 45. So we can use this now, we can rearrange it to work out what this missing angle of alpha is. So if we rearrange, we've got 400 sine alpha equals 50 cos 45. So sine alpha, or alpha if we take the inverse sine, will be the inverse sine of 50 cos 45 divided through by 400. And that gives us an angle of 5 degrees. And it's 5 degrees from the west. So if we wanted a bearing from the north, it's going to be 270 plus 5, so a north 275 bearing. So we've got the direction the pilot should be flying is the north 275, and now we need to work out what the resultant ground speed will be, so work out the value of R. So we use the vertical components to work out the angle alpha, so let's use this time the horizontal components. to work out the value of r. So the horizontal, it's the only component of this vector, so that's going to be equal to our value of r. And if we're setting left as our positive, so let's take the horizontal component from the plane, which is 400 cos of alpha, and we've just worked out alpha to be 5 degrees, so we can put that in there now. And then the wind speed, that's acting in the other direction, so it's acting eastwards. So we subtract that away, so subtract the horizontal component, which is 50 sine 45 degrees. And if we calculate that, that gives us our resultant vector is 363 knots.